Okay, let us continue. Our third talk is by Patricia Alonso Ruiz. And her title is The Trouble with Defining Perimeters in a Nested Fractal. So please.
Okay, well, thank you very much for the invitation, for the opportunity to be in this sort of space in the middle of nowhere. And talk to you about some recent results. This is joint work with Fabrice Baudouin from UConn. And one of the main questions that we wanted to address was how to make sense of the definition of perimeter for a set that is inside of a fractal. And I have chosen the title in a way that can be used as sort of a guide of the talk. So it has sort of three main pieces. The first one, I would say, is the word perimeter. So we will see in a second, we'll talk a little about perimeter in different ways. And then I'm going to just briefly recall what a nested fractal is. More specifically, we will talk about unbounded nested fractals. And finally, we will discuss what the trouble is with whatever definition we try to make sense of. And so to get started, I would like us to have a look first at what happens, say, with a very nice set in Euclidean space. So one like the one that I have pictured here. So if this set, say, this is in R2, and it's nice in the sense that, let's say, it has a very smooth boundary. So in particular, we can think of the boundary as being, we can draw it as just by using a curve. But the most direct or natural way to think of the perimeter of this set would be, well, let's look at the length of the curve that I have used to draw this set. And well, the length of the curve is nothing but the one-dimensional Hausdorff measure of the boundary. Now, of course, we can rethink this in higher dimensions, and we will see exact same thing in the sense that if my set is, let's say, a subset of Rn, smooth boundary, and everything is nice, now the perimeter, instead of being 1, it's going to be just -1, right? So if we think of, say, in 3 dimensions, we think of a set with a smooth boundary, well, the boundary is going to be a plane, so it would be the surface area of that, which is then the 2-dimensional Hausdorff measure. And so in general, right, this number that we are seeing there is nothing but the codimension 1. Oh, sorry, let's write this, codimension 1 Hausdorff measure of the boundary. And well, now we would like to have a look at what happens if instead of living in Rn or R2, we are living in a space that is fractal. So now we forget about the sort of ambient space we used to construct it and think that our world is now just really a fractal, and we are trying to we are looking at the set that lives within the fractal. So something like what is on the very right here. Let's make some preliminary observations. Yeah. So if we look at this set and think of what the boundary would be of the set, well, to me, the boundary is what touches the inside and the outside of the set, right? So in this case, if we are only looking at inside or outside, but within the gasket, the boundary would be just these points that are really touching the interior and the exterior of the set. Yeah. So I'm seeing it is a finite number of points. So my expectation, so to speak, I would expect that the boundary, this is just a finite set. And so somehow the boundary, the perimeter, if it ought to be something meaningful, it should be, well, at least some, maybe up to a constant. I would like this to be, so the perimeter of this set up to a constant maybe, but it should kind of tell me what the number of points of the boundary is. And well, in terms of Hausdorff measure, the number of points is the zero Hausdorff measure of the set. And so I'm trying to make sense of how does this fit the usual picture, right, of having the codimensional one Hausdorff measure against, now I'm seeing, I would like to see the zero Hausdorff measure. And so, okay, this is some sort of starting preliminary things, and we would like to have a look at what would be a meaningful way to precisely get this zero Hausdorff measure in a way that also fits other characterizations of perimeter that exist in classical settings. And so here is where our story begins. I would like to review a little of what are the sort of three main protagonists in this story. And to me, at least, everything is going to start with this observation by Gacciopoli, who was able to characterize the perimeter of a set in Rn, so any Borel set, in a way that it turns something like a very geometric quantity, as we have seen, the perimeter of a set, is able to express it in, to me, somehow purely analytic terms, namely like this. So let me write first. He is proved that the perimeter is going to go inside with the total variation. This is the total variation of the indicator function, measure of the indicator function of the set. And so what is the total variation? Let us recall ourselves what is that. So in general, for any function, so this specific function here is the indicator, but for any generic function that is in the space called BB, right, for bounded variation, so those that have their total variation bounded. So how is this defined? Well, this is defined as, well, we want to look at the variation of the function in some sort of weak way. And so anytime we define things weakly, we are looking into a set of test functions where we look at the variation, we move it, we shift it to the test function, right? So in this case, we are going to look at where we will integrate. I'm going to leave here my f without touching it and move the variation to a test function. And my set of test functions are going to be C1 with compact support and an infinity norm less or equal than 1. And the way to look at the variation is by looking at the divergence of this function. So this is the way how one generally defines the bounded variation norm of a function. The only sort of drawback that I see in this, for me, is precisely on this divergence, because if we try to think of what the divergence of a function defined as a Sierpinski gasketed, this is way less intuitive, at least. So it's not so clear how to define that. But well, thankfully, there has been enough people have been thinking about further characterizations, how we could talk about functions of bounded variation in more general spaces. And one of them, one of these characterizations is due to Korevar and Shine in 93, who proved the following characterization. So this is also up to a constant, which I am going to omit for now. So what they did was, okay, let's look now at this variation of the function in terms of seeing what the value of the function is at a point, and then seeing what happens in a small neighborhood. So we are going to look at balls with a radius that is getting smaller and smaller. So we would integrate, maybe we need some renormalization factor. And now we are going to integrate. And now, instead of looking at the variation, we look at taking some sort of weight average of this over the ball. So we are looking at the ball, radius r, and then looking at how the function varies in the vicinity of x. And the weight that we are going to put here is r to the n, simply because that's how the volume of the ball more or less grows. So this is the y dx. And okay, one thing that we will look at later on, and I want to already put this here, that this we don't see it, but we don't write it, but there is a 1 in this factor. So this is a characterization that I like very much, because there is no divergence there, and in principle I could make sense of all of these elements in, say, on the Sierpinski gasket or any general metric measure space. Of course, the question is and will be looking what is the what are the correct exponents, if there are any correct exponents in there. And well, we will focus on that one, so on this Korevar-Shine characterization. However, I want to give sort of a full picture of other possibilities that are there, since we also looked at those in the paper. And the other one is due to the work of several people. And instead of looking at, say, a metric measure theoretic way to describe the variation of a function, we're going to use Brownian motion for doing that. And we will get the following thing. So the B norm of a function is going to equal, so this is this theorem by all these people. Now I'm going to write really equal by, because the constant is easy, so it's just a square root over 2, square root of pi over 2. And now we will look, as I was saying, at what happens with Brownian motion. Instead of looking at small balls, we are going to look at where did Brownian motion go in a short amount of time. So now the limit that we're going to consider is as time goes to 0. So small time, hopefully short movement or space, and then so now the constant, not the constant, the scaling that we will get, this will be a square root of t in this case, which is we see this square root anytime we see Brownian motion in our n. And now we get sort of a similar expression. Now our integral is going to be, so we are looking at the variation of the function, but now we will see here the heat kernel. So this piece here, this PTXY, this is the Gaussian heat kernel, which is telling me what is the probability, so to speak, that Brownian motion goes from X to Y. So this one here, this is the Gaussian heat kernel. And well, of course, the question now is, okay, what happens if instead of being in Rn, by the way, let me say that these characterizations are perfectly fine as well if we are looking at a smooth Riemannian manifold with bounded curvature, for instance. But now the question now again is, well, what if I would like to replace my ambient space? So now what if my space becomes something pretty rough, something like this unbounded Sierpinski gasket that I draw here. So this is unbounded Sierpinski gasket. Or more generally, say an unbounded nested fractal. So let's have a look at what happens then. And so that we are on the same page, let us briefly say what an unbounded nested fractal is, how we construct those. And another way of thinking of that is like as a blow up of a planar nested fractal. So, okay, maybe let's say what are planar nested fractals, what are the main characteristics of those things? So, well, first of all, since I am saying it is planar, we are going to stay on things that can be embedded in R2. And we saw this already in the previous talk, so I was happy to see some of these. A planar nested fractal is the fixed point of where we have some number, finite number of contractions, in this case, similitudes. So all my contraction mappings have the same ratio. And this ratio, I will denote it by 1 over L, because the L, which is going to appear later on when we talk about proofs, this I would like to call it the length scaling. So length scaling. Okay, so in the case of the Sierpinski gasket, this L is going to be 2 because, well, I have my my contraction is bringing whatever this is. If this is 1, then this is a half. This is my new contraction. And the measure that we put here, we have also seen there are different measures we can write, but the sort of standard one will also satisfy this similar equality. So we want all the pieces. Well, we can choose what we give to each piece, but the standard one will be, well, let's give all the pieces the same weight and assume that the weight of the whole thing is 1. And then if I really want this to happen, what I would say is that, okay, so then the measure of each of these pieces is going to be 1 over m, so that when I add all of the m's, I get 1 again. And so that's the reason why this m becomes what I would like to call here the mass scaling. So those are sort of the main parameters, if you will, of a planar nested fractal. And now that I have sort of the bounded one, I would like to blow it up. And the way to blow things up is, how you do it. You take your original one and now you expand it. And we first expand it by a factor L of the one as the same as the length scaling. And then I expand that one again, which would mean I am actually doing raising it to any power, and then I'm taking just the union of all of them. So this is the way how one usually constructs the unbounded version of the nested fractal, and the measure carries is carried from the bounded one. So that one stays the same. So of course there are several properties that these nested fractals fulfill. I'm going to just only write some keywords just so that we have everything on this slide. So they are connected and they satisfy some symmetries. So when I'm writing symmetric here, what I am meaning is that they are symmetric with respect to each hyperplane we can build from two boundary points. So in the case of, say, the Sierpinski gasket that we were looking at, my boundary points are these three vertices, and so I would take two of them, draw a hyperplane, passes through both of them, and then just it should be symmetric with respect to this axis, and also this one and this one. And then what else do we have? Where we have the so-called nesting property, which means simply that if we take two cells, right, so two images of the whole thing, these two will be either completely disjoint or they will only intersect at a certain number of points that are images of the boundary points. And finally, our well-known, I would say here, open set condition must be satisfied as well. Okay, so now that we know more or less we have all these notations in there, we can try to see what would be our perimeter candidate. And let me put this maybe a little up here. Let's see if we can see it. Yeah, so we see on the very top this characterization by Korevar and Shine, and we said, okay, this looks like something we can use. We can only need to see what are going to be the correct exponents to put there. So for the perimeter, remember that Caccioppoli, well, maybe let's put it up there. Caccioppoli said perimeter is the total variation of the indicator. So we're going to plug in an indicator in this definition by Korevar and Shine, and then see what do we do with the exponents. So let me copy paste this. So let's copy what they did and paste here. So my perimeter, let's see, or the candidate for the perimeter is going to be, so we don't know yet, okay, but certainly we don't want to put this function, we want the indicator here. So let's put an indicator. And now, okay, well, what do we do with this n? Well, the n in our n was n, right? So how is the scaling of the volume scaling? So in this case, we can just turn it into I'm going to stop so you can think of it, and then the house of dimension. Another other question is about this one we mentioned before, right? So this one, what do we put in there? Yes, and I want to make this, let's make a quick observation here up. What could this one be? Yeah, so this was one, and another place we saw a one when we were speaking about how the perimeter looks like in the classical case. We said this is the codimension one Hausdorff measure. And so, okay, if this exponent should be sort of, or we can think of it as being the sort of whatever codimension something is. And now on the other hand, I go back to our initial thinking of how this should look like for on this unbounded Sierpinski gasket, and I'm seeing I have a 0 in there. If 0 now should be n-1, well, 0 is, what type of codimension is this? Well, 0 is codimension in terms of the h, right? Codimension the h Hausdorff measure, right? Because codimension n is like n-n0. And so that's the reason why I am going to think that this probably the best choice is going to be here in this case to also write the h. And it's not only just a heuristic, but in previous work with many other people, so Fabrice, Baudouin, Lichen, Luke Rogers, Nagesh, Amugarian, and Sasha Teplayev, one thing that we worked on with functions of bounded variation on fractals, and we did see that in fact it is true indeed that, and now let me make some notation and stuff. I'm seeing something that I forgot. We are not in our N anymore. Now we are in whatever the fractal is. My nested fractal. Let's call this thing here because it is pretty long. Let's call this M on ER or something. What we did prove is that if we are looking at functions, BV functions, so function of bounded variation on a nested fractal, so on a nested, what we are going to see is that the quantity, and now we are looking at lim-inf versus lim-sup, of this 1 over dh mfr less or equal lim-sup. So in this work, we were kind of only worrying about what functions are in the space or not. So that was more than enough for us. This is finite, and which is kind of reassures ourselves in our candidate. However, and now we come to the trouble and the main question of all this business, which is, well, here we were able to prove that these two things are less or equal than. So can we actually, if we want this to be true, we should be able to prove that these two things are the same. And that is where the trouble begins. Yes, so okay, so what's the trouble? Where we just said, okay, the question now, which is still not quite clear to us, does this limit really exist? Does the limit when r goes to 0 exist? And well, here's the answer. I'm not going to say yes or no at this moment, but just to give you a theorem. We will say yes or no at the very end, but there's this theorem, and this is this work with Fabrice, and this has just been published. And I'm going to write it for the specific case of the Sierpinski gasket, although we can do things for other examples. But so now if we take a set that looks like the one that is pictured here, where it has other things with other colors. So let's do this. So, okay, in SG. Yeah, and this looks really like that. So let's this be a finite union of cells. Well, then we find a bounded periodic function, theta, such that the following thing is going to happen. So remember that our candidate was this limit when r goes to 0 of 1 over dh, and then we have this functional on ER. And if we now even go back to the very beginning of our discussion, remember, we really were hoping this to be somehow related to the number of points in the boundary. But we're going to see that this is in fact the case. However, my bounded periodic function theta is going to pop up here. And so somehow this is telling me or hinting me at the fact that the limit will not really exist, because this quantity is going to oscillate. So the reason for this bounded periodic function being there is sort of canceling the oscillation, so that in the end I do get a limit that is really what we were expecting the perimeter to be. And since I still have 5 minutes because I'm writing by hand, I have time, just some time, to tell you a little bit about the proof, what goes in it. So let's talk about the main points of the proof. And in principle, so for the statement here, we are going to use renewal theory. It's following some ideas that, for instance, Handley had used to prove other results for functionals of the heat flow on Sierpinski carpets. But so in our case, how this is going to work is as follows. So remember, we are interested in the quantity in this function. Well, by using the properties of nestedness, we can actually rewrite this functional as the sum over pairs of cells, and I would like to call these boundary pairs. What are these boundary pairs? Well, these boundary pairs are nothing but, say, if we have a boundary point there, a boundary pair is one of the cells outside and the one that is inside. This is a boundary pair. This would be KB and KW, for instance. So I'm going to just rewrite it like that. And then I will see another functional, which is going to depend on these two of R. So what is this functional? This is nothing but as it was defined, the previous one. But then the first integral is going to be over one of the cells and the other one over the other one. Okay. So this Vx r, and then I have 1ex minus 1 dy dx. So this is sort of my first observation comes here. And my second observation is going to be that if I look at this function, and now make a rescale in the radius, and I rescale this by the scaling factor that I have, the length scaling. What I'm going to see is that I also need the mass scaling outside of the function. And so if I look at the quality, so this one equals this one, this is very much reminded me of some sort of renewal equation. And so now I can prove a renewal lemma. Well, using a renewal lemma will tell me something about how this quantity behaves as the radius goes to 0, and how it behaves is precisely in the way that we are stating there. So we are going to see r to the dh, and then here the lemma will give me the existence of this bounded periodic function in a way that this is how, and then there are some small order terms. And as we see, this is independent of the two little cells. So in total, what's going to happen if I read all of it, so this is maybe the third, if I read it all, what I am seeing is that, okay, M1ER is actually behaving like this whole thing. So maybe copy paste here. Yeah, this whole thing. But now we still need this part here. So we are adding over all these boundary pairs, but well, the number of boundary pairs is the number of boundary points. So that one is going to come into here. Yeah, So this is like that. And that will give me, after taking the limit, I'm just putting everything that's on the right and dividing everything by r and so on and so on. And this is where I am getting my limit. Now, just to finish off, so far, this renewal argument, like the general theory, the one thing that does not tell me is whether this bounded periodic function is constant or not. Well, if the bounded periodic function is constant, then of course the limit exists, right? There is nothing in there. However, and that is the final point I want to make, and this is now specifically in this case for the Sierpinski gasket, unbounded Sierpinski gasket, is that this function is indeed non-constant because we can find two different sequences of radia, so Rn and Rn tilde, such that when we look at the limit, so when the limit goes to infinity of these quantities, these are not going to be the same. Okay, and to give you just a little picture of how these go, well, let's make here Rn and here Rn tilde. If I think of this is the point in the middle, my first way of taking radia is going to be like this. So as you see, one of these radius covers two full little cells. And in the next generation, this is Rn, so Rn plus 1 is going to just go one level less, and it will take full two little cells here. Yeah, and so on and so on. Whereas for the tilde one, what we are going to do is, instead of taking for the first one as we did before, I am going to go and take also with me the first smaller cell that is touching the greater one. I mean, I don't know if this, I hope this is, one can see it. And so that in the next generation, right, instead of just only taking these two as we did before, I would also take a little piece of here and a little piece of here. So this one would be my Rn plus 1. So if we perform computations, and now we are really looking into the specific construction of this example, we can find out that these two limits will be different because we can compute them pretty explicitly. And with that, you tell me the answer to the question is, of course, no. Which is still kind of very interesting because I don't want to put a sad face, because in fact it was a good face for us. It was some non-trivial question to answer. I think that's all I wanted to say, so thank you.
Okay, thank you very much. Are there any questions, comments?